displays the well-known phenomenon. However, if a row of dominoes gradually increase in height, we should investigate how the energy transfer takes place and determine limitations to the size of the dominoes. So, let me give you an outline of my presentation. First, we start with the introduction, with the principal and important parameters for this effect. Then we have a theoretical approach, where we use Lagrange formalism. Then we go on with the tilting conditions for the domino. Then we have the array and the friction of a row of dominoes, and then finally the limitations. Afterwards, we come to the experimental part, where we have a falling experiment, a comparison with our theoretical approach. Then we have the critical cases and the increasing dominoes as you see here in the front of you. And at least a conclusion with references and an overview. So, if you have a row of dominoes, as you can see here in the back, we have to displace the first domino stone over a critical angle. And if it is displaced over a critical angle, it falls till it impacts at the next domino stone. And if the impact energy at the next stone is big enough to tip this domino stone, the so-called domino effect occurs. So we can say that the impact energy must be bigger than the energy which is necessary to tilt the domino stone. This energy is the energy which is necessary to lift the center of mass over the vertical. So, if the domino impacts at the next domino stone, we have a force. And the force can be split up in two components, one horizontal and one vertical component. And the horizontal component must tilt the next domino stone. And if this is correct, we will achieve such a domino effect, as you can see here in front of you. Tilt, 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 tilt. Okay, well, then let's go. So, what are the basic ideas or the basic limitations to the dominoes? Of course, the height must be bigger than the thickness of the dominoes, otherwise it will be something like a cube. And the distance must be bigger than 0 and smaller than the height so that it impacts at the next domino stone. And, of course, this is the contact angle, and here we have the critical angle. And due to that, we have such a high compressive strength from our wood material, we have an elastic impact because we don't have plastic deformation. And so we say that we have an elastic impact. Now, what we are doing is we don't increase the domino just in one dimension, in height, we also increase it in all three dimensions. I will come later to this point why I just increase this in all the three dimensions, not just in one dimension. And also we found out that a domino stone has a height of 5.6 millimeters. And the width of the domino stone is half times the height, and the 4 times the thickness of the domino stone is even again the height. And there are also world records in this domino, so-called domino toppling. So the world record is at around 9 meters. And now what happens if the domino rotates? Of course, we have to first calculate the moment of inertia. The moment of inertia for a normal cuboid is given with that formula. It's well known. But actually, our domino stone don't fall around its center of mass, it falls around another axis. So we have to use Steiner's theorem to calculate the moment of inertia for our domino stone. And here you can see that the moment of inertia for a domino stone is 4 times higher than for a normal cuboid. And to solve the equation of motion, we use energy conservation, especially with Lagrange formalism. So we have here the potential energy, and here the rotational energy, as you can see here. Then we apply the Lagrange formalism, as you can see here. This is simply the rotational energy minus the potential energy, express the height of the center of gravity independence of the angle phi. Then we use the Euler-Lagrange equation, then came to this differential equation. As you can see here, we have the angular acceleration, here we have the sum of constants, and here we have then our angular dependence. And we solved then this numerically to prove it with our experimental values. To prove this, we made just a simple falling experiment and made then a binary analysis of this falling and fitted it over our theoretical numerical solution. As you can see here, it's the motion fall of the domino. And here we have the proof of our theoretical approach. So we have here the theoretical prediction, and here's the angle, and here we have the experimental values. So what we also got from our energy conservation was the angular velocity independence of the angle phi, as given with that formula. You can see here the increase in the angle. And however, we're now searching for an impact of the strongest horizontally component of the velocity, so that we have the strongest horizontal impact at the next domino stone. And this was found for our domino stone at an impact angle of 50 degrees. And we got this from plotting that formula. And now, what happens at the impact from the dominant stone? Of course, we have a significant impact energy, which is simply the kinetic energy. Then we have to tilt the next dominant stone, so we have to displace the diagonal over the vertical so that the next dominant stone falls. So we have here the energy which is necessary to tilt it. And so we come to a threshold. And if the impact energy is bigger or equivalent than the energy which is necessary to tilt, we assume the dominant effect. And now what happens if we plot this formula and increase just the height? Of course, the mass will increase, but actually the critical angle will decrease. So we assume such acceleration effect. And as you can see here, the mass increases and also the critical angle decreases, so it becomes unstable. So an increase in height is not a limitation. And we just proved this by made a dominant stone, the next dominant stone 5 times higher, with all the same other dimensions. So it's here, it tilts, and it tilts the next dominant stone. So actually, the more complex, interesting form is plot is if you also increase the thickness of the next dominant stone. We assume this in such a three-dimensional graph. As you see here, with here the increase in height, here we have the increase in the thickness of the next dominant stone. And here the line was that the height is 4 times the thickness. And from this we then got our dominant limitation. Okay, well then, our theoretical model goes further on. We also were interested in the angular dependence of several dominants. Of course, an array of dominants is also influenced on this effect. So we've calculated what happens if we have an array of dominants. Here we have the angular dependence. And also, what we are interested in was the friction of the dominant. So of course, we have a significant friction energy. Then we express the normal force acting on the dominant, and then for a friction energy, this long curve. And if you may consider the formal formula, as it is here, we have to insert this formula in that equation. And as you can see, this is quite not very solvable. So we made an approximation for this one. And then we actually said that the energy is decreasing linearly, so the force is constant. And then we got for the distance act that formula, for the tilt energy that formula, into the critical angle in this formula, and then got for friction losses 10% of the energy from the impact. So we're around 10% loss from the impact. And we also considered air resistance. And we found out that air resistance is neglectable because air resistance is at around 0.02% of the whole friction, of the whole energy. So now we came to the final formula with here the sum of all impacts, so the sum of an array, then minus the energy which was necessary to tilt these dominant stones. Then on the right side, this must be bigger than the energy which is necessary to tilt the dominant stone, plus the friction losses. So without friction, we came to a factor of all three dimensions of 1.06 of increase. But actually, we have friction losses, so we increased our dominant stones with a factor of 1.5, so that we consider these friction losses. And then our next step was to prove these critical cases experimentally. And as you can see here, we at first, you may see it, to maximize the ground friction so that we don't have a slip backwards from our dominant stone, introduce a non-slipping mate, as you can see here. And now let me show you 2 videos. At the bottom without non-slipping mate, and here at the top without non-slipping mate, and at the bottom with a slipping mate. You can see this clear result. We have at first a slipping back, and at the bottom you don't assume a slipping back of the dominant stone. Actually, we also consider different angle of attack at the next dominant stone with different distances. So at first this distance is too large and this distance is too small. So actually in both cases the domino effect won't work. So we actually have to search for an impact with the strongest horizontally component of the force. And now what happens if we have an array of dominoes? Of course this seems trivial, but actually you have to consider this if you build your theoretical model. So if we have here 2 dominoes, it won't work. But actually if we have an array of dominoes, you can clearly see that it works perfectly, this tilting process. And now from this theoretical approach and from considering these critical cases, we then came to our final dominoes, as you can see here in front of you, or here at the video. So, and I will now show you, if someone has not seen this video, this live experiment, you can see here this perfect tilting process. So now I'd like to come to my conclusion of this problem. Actually, we have we have considered the increase in height. So we've considered what happens if we increase in height. We have seen that this dominant stone becomes unstable. So of course, due to that, the critical angle decreases and the height increases with the increasing mass. So this was once again the graph with increasing height. We also considered how the energy transfer takes place with an elastic impact at the next dominant stone, and we have a significant impact energy. This impact energy must be bigger than the energy which is necessary to tilt the dominant stone, so that we assume this dominant effect. And finally, we then assume what happens if we have increased orbital thickness. And an increase in thickness will also increase the critical angle. So we then assume this three-dimensional graph. From this graph, we then assume our dominance. And so I'd like to come up with my conclusions. We built a theoretical model where we include the Lagrange formalism, calculate the equation of motion, then we have the tilting process, what happens in this tilting process, then we have considered the friction between the dominoes, also considering the array of dominoes, how does this change. Then we came finally to our limitations. We proved the critical pace experimentally, and of course, if you take a look at these formulas, so if you have, for example, this domino stone and that domino stone, you can calculate with that formula how many domino stones we will actually need in between them till this domino stone. So actually, if you have a skyscraper, such a small domino stone, you can calculate how many domino stones we will need to tilt this skyscraper. So actually, ladies and gentlemen, I'd like to thank you for your attention, and if you'd like to go further reading, take a look at my references. Thank you very much.
We have time for questions from the opponent.
Oh, well, thank you for the nice report. Did you also vary the material of your domino?
Well, actually, there are many variables to vary. So actually, varying the density or the material of the domino will just have an increase in mass, a linear increase in mass. It's trivial. And
yeah, but did you vary the material? Did you use steel or something like this?
Well, actually, the problem with that is, so if you try to
yes
make
or no?
No, we don't consider this with different materials because actually
yes,
different materials
that's enough. Did you also consider the wear of your dominoes?
Excuse me? Once again.
The wear of your dominoes that they get used, that the edges get round and there may be a not so good collision between the dominoes.
Actually, do you mean that we flatten the edges of the domino?
Yes.
Actually, not, because the definition of the domino is a cube. Like, the cube should not be flattened.
Yeah, but your dominoes have this flattened and the edges. I think so.
Well, actually, if you can later take a look on, we have no.
Okay, we'll discuss this. Did you also vary the material of your ground as you showed us before in the video?
Yeah, actually, you see this in the video.
Yeah.
We have varied this material. Optimize this ground friction. We've introduced such a long split made to maximize the ground friction so that we don't assume a split backwards.
Okay, did you also have an error of your experiment?
In what dimension? What do you mean?
For the increasing
actually,
effect.
you see the error if you take a look at the presentation. So we have here the error. So here we are. Here we have the error of the falling process. Yeah.
Okay,
so
thank you.
Okay, thank you very much. The time for questions is over, and now we have the